Section: Introduction. In this section, we explore how reinforcement learning, RL, has become a valuable tool for improving the reasoning abilities of large language models, LLMs. We have seen RL applied effectively in areas like mathematics and code generation, where it helps models develop complex reasoning skills based solely on problem examples and their associated rewards. Formal theorem proving is particularly interesting for us because systems like Lean and Isabelle can verify mathematical proofs step by step, rewarding models only for completely correct solutions. This automated verification process makes formal mathematics an excellent environment for testing RL algorithms. A key challenge we face is creating RL algorithms that do more than just refine existing solutions. We want our RL-trained model to tackle problems that cannot be solved by merely sampling more from the original model. Our initial experiments reveal that existing RL methods, particularly Group Relative Policy Optimization, GRPO, have limitations. While GRPO can enhance accuracy for single samples, it often does not improve and can even worsen performance metrics when we consider multiple samples in theorem proving. We believe that to enhance performance, we need to increase the chances of generating less likely but correct responses. To illustrate this, we created a simple model that shows GRPO tends to favor high probability responses while overlooking rare but correct ones, which reduces diversity and overall performance. To counter this, we propose an unlikeliness reward that gives more weight to less likely correct outputs. This adjustment significantly alters how GRPO learns from these less likely paths, leading to greater output diversity and improved performance across various metrics. Additionally, we discovered a surprising connection between GRPO's tendency to sharpen distributions and a hyperparameter we often overlook: the number of epochs in proximal policy optimization, PPO, per batch. By increasing the number of epochs, we can provide more training signals for less likely solutions after the more likely ones have been saturated. Tuning this hyperparameter, alongside our unlikeliness reward, offers valuable insights into how we can optimize our approach. We demonstrate that our revised training method significantly enhances performance metrics across different sample sizes and outperforms standard expert iteration. By combining the unlikeliness reward with our findings on PPO epochs, we create a comprehensive strategy for reinforcement learning in formal theorem proving. We apply this strategy in Lean, resulting in a fully open pipeline that competes effectively with existing models like DeepSeek Prover v1.5 RL on the Mini F2F test benchmark. In our study, we focus on training a language model for formal theorem proving, aiming to generate valid proofs within a proof assistant. We utilize Lean, which is based on dependent type theory and supports the construction and verification of mathematical proofs. Our dataset consists of theorem statements, each with a natural language description and a formal expression in Lean. The verifier, which also serves as our reward function, provides feedback on whether a candidate proof is successful. To assess the prover's performance, we use the pass at n metric, which indicates the likelihood that at least one of n independently sampled proof attempts is successful. This metric is practical for generating and verifying multiple proof attempts to find at least one that works. We define the empirical pass at n for a single theorem and calculate the average pass at n score across our test set, which helps us understand the effectiveness of our RL approach. A high pass at n score suggests that we are likely to receive positive rewards when sampling multiple completions for each problem. Section Summary. In this section, we explore the application of reinforcement learning, RL, to enhance the reasoning capabilities of large language models, LLMs, in formal theorem proving, highlighting the limitations of existing algorithms like Group Relative Policy Optimization, GRPO, in improving pass at n metrics. We propose an unlikeliness reward to boost the learning of less likely correct responses and demonstrate that tuning the number of PPO epochs can further enhance performance, leading to a more effective RL training recipe for generating valid proofs in the Lean Proof Assistant. Section: Reinforcement Learning. In this section, we utilize Group Relative Policy Optimization, GRPO, as the basis for our reinforcement learning experiments. GRPO, which has been effectively used to train models like DeepSeek R1 and DeepSeek Prover v1.5 RL, shows strong results in both informal and formal contexts. It builds on proximal policy optimization, PPO, but does not use a critic model. For each question, GRPO samples a group of outputs from the current policy and aims to maximize a specific objective. Unlike PPO, GRPO calculates advantages by normalizing rewards within the sample group instead of using a baseline from a critic model. We define the reward for each output and compute the advantage by taking the difference between the reward and the average reward of the group, divided by the standard deviation of the rewards. If all or none of the samples solve the problem, the advantage is zero, leading to no gradient updates for the model parameters, except for a specific term. To enhance efficiency, we use a method similar to dynamic sampling, where we keep a buffer of recent samples with non-zero advantages and only update the model once this buffer reaches a certain size. Next, we explore how GRPO performs in formal theorem proving. Our setup mirrors previous work in terms of model and hyperparameters, but we create our own dataset since the original is not available. Our dataset, the Lean Workbook, consists of around 140,000 theorem statements auto-formalized from natural language math problems. We select a subset of 10,000 solvable problems, ensuring they remain challenging. We also include additional problems from another dataset, holding out 200 theorems for validation and using the rest for training. We implement GRPO using a specific framework and make adjustments to accommodate reward feedback from the Lean REPL. Our base model is DeepSeek Prover v1.5 SFT, and we adopt certain hyperparameters, adjusting the learning rate for stability. Due to computational limits, we train for only one epoch and restrict response lengths to 512 tokens. Our findings indicate that GRPO does not improve the pass rate at larger values. While it significantly enhances the pass rate from 1 to 16, the improvements taper off for larger numbers. This suggests that GRPO is good at boosting the likelihood of already probable solutions but struggles to introduce new high-probability solutions, which aligns with previous findings. We then consider whether reinforcement learning can enhance the pass rate at larger values. We argue that to improve the pass rate for large numbers, RL must increase the chances of low-probability correct solutions. We express the expected pass rate mathematically and analyze how RL training impacts the initial probability of solving a problem. Although predicting the exact outcome of gradient steps is complex, we estimate that maximizing the GRPO objective can lead to improvements in the model's accuracy. Ultimately, we conclude that to increase the pass rate for large values, the training algorithm must specifically enhance the probability of low-probability correct solutions. Section Summary. In this section, we utilize Group Relative Policy Optimization, GRPO, for our reinforcement learning experiments, which enhances model performance in theorem proving by normalizing rewards within sampled outputs. However, while GRPO improves the likelihood of probable correct solutions, it struggles to elevate the probability of low-probability correct solutions necessary for significant gains in pass at n for larger n values. Section. Does GRPO reinforce unlikely solutions? In this section, we explore whether GRPO reinforces unlikely solutions. Our previous analysis and observations indicate that GRPO does not seem to enhance low-probability correct solutions effectively. To investigate this, we analyze training samples from the first 800 problems, calculating their probabilities under both the initial model and the final GRPO trained model. We denote the ITH training problem as x_i and its corresponding solutions as y_i_j. We compute the probabilities for each solution given the problem for both models and are particularly interested in whether the ratio of the GRPO probability to the initial probability is close to 1 plus a small value, especially when the initial probability is low. We notice that the raw probability ratios vary greatly and contain extreme outliers, making direct analysis challenging. Instead, We rank the solutions based on their initial probabilities and use this ranking to assess the likelihood of being uplifted by GRPO. For each rank, we calculate the uplift rate by averaging over positive samples. Our findings show a clear positive correlation. GRPO tends to increase the probability of high probability correct solutions, while low probability positive samples, which are crucial for improving performance at larger N, are rarely uplifted. We confirm this behavior in a controlled environment and label it as rank bias. To address this issue, we introduce the unlikeliness reward, a modification to the reward function that discourages reinforcing high probability solutions. For a group of samples, we denote the rank of each sample under the current policy. We adjust the reward by applying a penalty to higher rank solutions, which enhances the relative advantage of rarer positive samples. Incorrect solutions remain unaffected, receiving a reward of 0. We set the penalty strength to a fixed value in our experiments and ensure that no batch is dominated solely by this reward. Additionally, we find that increasing the number of optimization steps per sample helps mitigate rank bias. Standard implementations typically use a single optimization step, which can lead to biased updates. By taking multiple steps, we can focus on low-rank samples that are still unclipped, thereby amplifying the learning signal for these samples. However, this approach can slow down training and introduce instability, so we prefer the unlikeliness reward as a more direct and efficient solution to tackle rank bias. Section Summary. In this section, we analyze the limitations of GRPO in uplifting low-probability correct solutions, finding that it tends to reinforce high-probability solutions instead, a phenomenon we term rank bias. To address this, we propose an unlikeliness reward that penalizes high-probability solutions, thereby encouraging the optimization of rarer, low-probability samples, and we also discuss how increasing optimization steps can help mitigate this bias. Section: Experiments. In this section, we describe our main experiments using the training and validation datasets. We compare various GRPO variants with different hyperparameter settings, as summarized in a table. We found that increasing the KL penalty helps prevent a decline in pass at N, but this change alone did not significantly enhance pass at N, as discussed in the appendix. All other hyperparameters remained constant. For our results on pass at N, we present the performance of GRPO variants evaluated on the validation dataset. We observed that adding the unlikeliness reward significantly improved pass at larger N values, with only a slight trade-off for pass at 1 and pass at 2. Additionally, increasing the number of PPO epochs also improved results, although it increased training time, as noted in the appendix. We tracked the cumulative accuracy of 32 samples generated per problem during training, including the baseline performance of a static model. Our table shows that all GRPO variants outperformed the static model, with GRPO unlikeliness 2 solving the most problems. Since we trained for only one epoch, each example was effectively new at the time of sampling, indicating good generalization. In our analysis of rank bias, we repeated our earlier analysis by calculating the U_J metrics for each GRPO variant over the training samples. The results showed significant changes in GRPO's behavior, with GRPO unlikeliness 2 reversing the original pattern and favoring low-probability solutions. We also demonstrated that the unlikeliness reward helps reduce rank bias in our controlled environment. In GRPO epochs 2 and GRPO EPO CHS3, while some bias remained, the overall reinforcement strength increased, uplifting low-probability solutions. For sample diversity, we monitored the number of unique proofs generated at each step. GRPO unlikeliness 2 displayed unique behavior, where diversity initially decreased but later recovered, unlike other variants that showed a steady decline. This suggests a self-correcting mechanism where dominant solutions are penalized, allowing less likely correct solutions to emerge. We also found that higher PPO epochs consistently increased sample diversity, up to 4 epochs, where training became unstable. This might seem counterintuitive, as more optimization steps typically move the model away from its initial distribution, but it aligns with our earlier findings. Higher PPO epochs indirectly boost rare solutions, reducing the sharpening effect usually caused by GRPO updates. Finally, we evaluated GRPO unlikeliness 2 in a large-scale experiment, training it on a dataset of 11,000 theorems, which is a more challenging subset of Lean workbook, ensuring we excluded theorems in the validation dataset. We assessed the resulting model on the mini F2F test benchmark and the validation dataset. Our results indicate that GRPO unlikeliness 2 achieves competitive performance compared to DeepSeek Prover v1.5 RL on both datasets. In the related work section, we note that automated theorem proving has seen advancements with transformer-based provers interacting with proof assistants. Subsequent research has developed models that generate proofs step by step or produce complete proofs auto-regressively. Recent studies have explored various approaches in LLM-based theorem proving, including inference time algorithms and informal reasoning to guide formal proofs. Our focus is primarily on post-training theorem provers using reinforcement learning. We also discuss expert iteration for theorem proving, which alternates between search and learning and has become a dominant approach in recent research. While the use of general reinforcement learning algorithms in theorem proving is less explored, some notable exceptions have shown that GRPO can enhance models using additional theorem statements and verifier rewards. Recent works have adapted techniques from OpenAI and DeepSeek to train reasoning models for theorem proving, achieving state-of-the-art performance. Lastly, we address the issue of RL's performance in multi-sample scenarios. Previous studies have indicated that RL with verifier rewards tends to concentrate outputs around correct answers already present in the base model, leading to improvements at small n but declines at larger n. We are the first to attribute RL's poor multi-sample performance to its inability to reinforce low-probability samples and propose a straightforward solution to enhance pass at n performance.